Can you? Thanks. Okay, so once again, thanks for the invitation and for putting together this wonderful program. So I will be talking about the Superconformal Bootstrap program now applied to four-dimensional series with either n equals 2 or n equals 3 supersymmetry. And so during the lecture, I mentioned that when you were studying the crossing equations for n equals 4 superbeing mills, at some point, there was like a subset of the crossing equations that looked simpler and we could actually solve. And I didn't really say why. So in this talk, I will explain how this comes about, how you can basically carve out inside any four-dimensional series with n equals 2 subsector that is isomorphic to two-dimensional chiral algebra, that is the left moving side of a two-dimensional CFT, and how, so that was what was giving you this amazing thing that the crossing equation just decoupled from everything else and looked much simpler. So let me get started. By now, you know what we are after. So the first question we really want to ask is what is the space of consistent superconformal field series? So let me restrict to 4 dimensions. I've already said that if you restrict to maximal supersymmetry, then you believe you have the complete catalog of series, n equals 4 superbeing mills is all there is. But the minute you go to half as maximal supersymmetry, then there is a vast zoo of known series that keeps growing. And many of these series lack a Lagrangian description, and so we have a few tools to actually tackle them. For the bootstrap, this should not matter, and that's why we are motivated to look at n equals 2 series using the bootstrap. And even though this space is large and keeps growing, there is some structure to it. So one thinks one can actually stand a chance of organizing the series a bit better, and I will show what we have done in this direction. But very recently, we were actually given a case in between. So a little over 2 years ago, Garcia Echevarria and Diego Regalado constructed the first examples of n equals 3 series. So series which have only n equals 3 supersymmetry that is not enhanced to n equals 4. And this provides kind of a case in between that is more constrained by symmetry, but not so constrained that we already have a catalog, and so there is a large number of n equals 3 series. Again, they're non-Lagrangian. Lagrangian series with n equals 3 symmetry automatically enhanced to n equals 4, but this doesn't matter for the bootstrap because we just care about the symmetries, and n equals 3 is a lot of symmetry. So this would be the first step, and this is what I will focus in my talk. But then, of course, after you have the complete catalog, if you could ever get the complete catalog of symmetric field series, you'd like to start solving one by one. And so that would be the other goal of the bootstrap. And for that, Pedro will tell you how much progress you can make with this, in some sense, the simplest non-Lagrangian n equals 2 SCFT. And okay, so let me focus on this thing. As by now you know very well, we will always take the conformal field series to be defined by a set of local operators and other correlation functions, so we will not consider any type of non-local operator. And the game is really to use the constraints of unitarity and associativity of the operator product algebra to place constraints on these quantities. And so you just saw in the previous talk that we do this by looking at the crossing equation. So if you take a 4-point function, it shouldn't matter how you do the OPE decomposition, either like so or like so. And this gives you an infinite set of constraints for all possible 4-point functions in the series for an infinite set of data. The set of all operators on all these numbers that appear here, the 3-point couple. Okay, so now you add supersymmetry, and then what? You know that, so you have a bigger symmetry, and now operators, your conformal families will now be related by the action of supercharges. So this organizes operators in a bigger family, but this is just still a finite reorganization because each superconformal multiplet will have a finite number of conformal multiplets. And so you could complain that this is just a finite reorganization of an infinite amount of data, and it will really not buy that much. But still, we are spoiled by supersymmetry to expect exact results. And we could ask, is there a solvable truncation of the crossing equations if you add enough supersymmetry? And the answer turns out to be yes, in 4 dimensions, if you have n equals 2 or more, and also in these other 2 cases. And so then, if you want to apply the bootstrap program for series that fall in this class, then what you should do is first solve this solvable truncation, this subsector, and then do the full-blown numerics, because you still care about more than this particular subsector. And for that, I will point you to Pedro's talk. So I will focus on this step 1. So let me first tell you how it comes about, this subsector. So as I've said, I want to organize operators in representations of the superconformal algebra. So on top of the operators are labeled by the scaling dimensions and the spin, and now I'm going to consider series that have n equals 2 supersymmetry. And so they will have on top of that an SU2R symmetry that I'm labeling by big R, and a U1R symmetry. If I have more supersymmetry, I will just take this as an extra stuff. So I will always think about n equals 2 series, and if there happens to be n equals 3 or n equals 4, then there is some extra conserved things that I'm not seeing right now. And so this is what I am denoting by this F. It could be a flavor symmetry that is some global symmetry that commutes to the superconformal algebra, or it could just be that operators actually are organizing in a bigger structure that is the bigger supersymmetry. So now what is your claim? The claim is that, let me pick a plane. There is no reason, no specific plane is preferred. I just select a plane out of nothing. And now let me put some coordinates on that plane, z and z bar. And now I'll restrict the local operators to lie on this plane. Again, there's nothing physical that forces the operators to be on this plane. I just decide to put them there. And so I get correlation functions that depend on the complex coordinates on the plane. Now I'm going to consider very special operators, in particular operators that the quantum numbers obey this particular relation here. And so they are transforming non-trivially under SU2R. So this is the label I'm putting here. This I is an SU2R label. And I'm going to do something funny, which is to contract this SU2R index with the vector ui that depends explicitly on the z-bar coordinate. And now the claim is that what you get is a meromorphic function of z. So the z-bar dependence drops out. And this would be just the correlation function of a 2D parallel algebra. So why does this happen? So this subsector is obtained by passing to the cohomology of a certain nilpotent supercharge. And I'm omitting the indices, but this is supercharge is a sum of a normal Poincaré supercharge and a conformal supercharge. So because of this conformal supercharge, you see that the cohomology class.
Sorry, a question. Yes. Yeah. So these U functions you know a priori?
Yes, I will give you explicitly in an example. They are totally fixed by this procedure. So yeah, okay, I will show you in a second. So because of this S, the cohomology at the origin and away from the origin will look very different. And so let me start by looking at because this does not commute with translation. So now let me start at the cohomology at the origin. Then I should ask, are there operators in the cohomology? And yes, there are the operators that obey this relation are precisely the ones that appear in the cohomology. And now I want to be able to translate my operators away from the origin in z and z bar while preserving them in cohomology. So on the plane, and I have an SL2 and an SL2 bar. This is just the global conformal algebra on the plane. And I am free to translate in the z direction because it actually, the generators of the SL2 commute in this supercharge. And so if I translate an operator that is in the cohomology in the z direction, I will preserve it in cohomology. But the SL2 bar does not commute with Q, and it's also not Q exact. So if I try to translate just naively an operator in the z bar direction, they stop being in my cohomology. So what should I do? This is where this vector comes in. As I twist the operator away from the origin, I must rotate it in SU2R space. Remember, this I is an SU2R index with an explicit z-bar dependence. So the precise statement is that the diagonal subalgebra of this SL2 bar and the SU2R is Q exact. And so I'm free to do these translations by these twisted translations. And then the anti-holomorphic dependence drops out. So I realize this is a bit technical, so let me show you an example where you also see what the UI is. So I start at the origin. Let me look at the simple thing. Let's look at the free hypermultiplet. And the complex scalars in the free hypermultiplet are in the cohomology. These guys are doublets of SU2R. So this I runs over 1, 2. There are 2 of them. And now UI is explicitly given by this. So when I set z bar to 0, I'm just picking the highest weight of the doublet. But when the z-bar dependence appears, then I'm forced to include the lowest weight. So this is how I define my twisted translated operators. Naively, they would depend both on z and z-bar. So let's do this. I just get the q at z-bar, and then when z-bar is non-zero, I'm forced to introduce here the lowest weight, and the same for q tilde. Okay, and now let's consider an OPE. So I take the OPE of these two guys, and for simplicity, I'll put this guy at the origin. So what I get is this. This is the only, so at the origin, I just have a q tilde, and q tilde will only have a non-zero OPE with q tilde star, so I pick up this cross term here. And now the OPE, I know it, there's an explicit z-bar, and you get something that depends only on z, so you see how the z-bar dependence dropped out. So now you can go on, which other operators are in the cohomology? Well, universal multiplet you should expect to have in any theory is the stress tensor. The stress tensor is not in cohomology, but it sits in a supermultiplet, so it sits with other multiplets in the same superconformal multiplet. And there's another operator in this multiplet that is in cohomology. It's actually the SU2R current. And if I do the same thing as I did in the previous slide, I will find this OPE, which you will recognize as the OPE of two-dimensional stress tensors. But this OPE was fixed from four-dimensional data. You see this C4D here. So now I can see that my chiral algebra will have a stress tensor. So the global SL2 will enhance to Virasoro, and the level, the two-dimensional central charge, is fixed from this relation in terms of the four-dimensional one. And it's actually negative, so yeah, I will get a non-unitary chiral algebra. So what else? So you can go through the list of all multiplets, but there are a few that are more physically relevant. For example, let's say I have a theory with a flavor symmetry, some symmetry that commutes in the superconformal algebra. Then there will be a multiplet that contains the flavor current. Again, the flavor current itself does not make it to the cohomology, but someone else who lives in the same multiplet will. And this will give you, unsurprisingly, a flavor current in the chiral algebra. So in 4 dimensions, if I have a flavor current, the two-point function of a flavor current is something physical. It has a number that is this K4D. It's the analog of the central charge for the flavor symmetry. And then when I do the same procedure as before, I get a two-dimensional OPE, but now I can read the two-dimensional level, the two-dimensional flavor central charge, in terms of the four-dimensional one. Again, it's negative, so I get, another reminder that my two-dimensional chiral algebra is non-unitary. And we could go on and see what other multiplets appear, but let me ask now, what happens if I add more supersymmetry? So you notice that so far I have that a single superconformal multiplet contains one operator that comes to the cohomology. So in this procedure, I used up all my supersymmetry and there's no supersymmetry left. Each four-dimensional superconformal multiplet contributes with one operator to the chiral algebra or with none if it's not in the cohomology. But now if I have extra supersymmetry, then some of the extra supercharges will actually commute with this funny Q that I pass to the cohomology of. And so if each superconformal multiplet will now give you more than one operator. So for example, if you have for the n equals 4, you get a small n equals 4 chiral algebra. And if you have n equals 2, you get n equals 2 supersymmetry in the chiral algebra. So let me again revisit the stress tensor. I had told you that the stress tensor multiplet of an n equals 2 theory would give me the stress tensor in the chiral algebra. But now there are these extra supercharges that I'm putting Q and Q tilde that commute with the thing I pass to the cohomology of. And so this guy actually comes in its own multiplet, and it's not the primary, it's the descendant, so you can build your way to it starting from another operator. And this is guaranteed to be present, this n equals 2 stress tensor supermultiplet, now in the chiral algebra, is guaranteed to be present in any local n equals 3 SCFT. So now let me start making trivial statements in 2D. So I have a two-dimensional chiral algebra that happens to have extra supersymmetry. Let me focus on n equals 3, so it has n equals 2. So I know that this whole thing is there. Let me call curly J the whole multiplet in superspace. Now, a trivial statement in 2D is that the four-point function of these guys is completely fixed in terms of the two-dimensional central charge. So I actually know this whole four-point function in the chiral algebra. And Now let me keep making trivial statements in 2 dimensions. I can decompose this 4-point function in superconformal blocks in the chiral algebra, and I get a bunch of OP coefficients of 2-dimensional operators that are being exchanged in this chiral algebra. Now, the non-trivial statement comes when we remember that each 2-dimensional operator actually came from a 4-dimensional one. And so these OP coefficients should allow me to obtain OP coefficients in the 4-dimensional parent theory. So I should lift these things to 4 dimensions.
When you say 2D super blocks, so these 2D theories are not unitary. They are just non-unitary chiral algebras. So how do you do representation theory? I mean, like, it's not the usual unitary representations.
They're non-unitary in a very simple way. Some operators get negative norms, but I always have positive dimensions, for example.
Okay, and you do, like, whenever you get a null state, you truncate.
Yes, we always remove null states, and I should point out that I am not using Virasoro blocks. I will use just global SL2 blocks and the global part of the superconformal algebra. Because if you try to organize operators in Virasoro representations, you end up being forced to mix different 4-dimensional multiplets, so you lose the notion of how to lift it to 4 dimensions. So all I'm saying here, these blocks, I mean just the global part of the superconformal algebra. So I get all these 2-dimensional OP coefficients that I can now lift to 4-dimensional ones. But while the 2-dimensional theory was non-unitary, the 4-dimensional theory is. So I should still impose that the 4-dimensional theory satisfies unitarity. And in doing this lifting, I had to make some mild assumptions. I assumed that I had an interacting theory with a unique stress tensor. Okay, but this is not guaranteed. Not all these numbers will be positive. And actually demanding that all these numbers are positive will give you a new unitarity bound for 4-dimensional series with n equals 3 supersymmetry. So this is the bound you get. And now the second question you ask when you see this bound, first question you ask is it actually saturated by any theory we've already encountered? And the answer turns out to be no. The simplest theory that is an n equals 3 theory that doesn't enhance to n equals 4 has a quite larger central charge. So now, okay, what's up? Why haven't we found this theory? Similar bounds for n equals 4 and n equals 2 theories were actually saturated, and Pedro will talk more about that. So what's wrong with this number? Is there something wrong with it? So let's fix our central charge to be this. And now we know this OP in the chiral algebra. So we know all these operators are being exchanged. Right now I was just looking at the OP coefficients, but I actually know the operators. So now let me try to lift these operators to 4 dimensions and see what happens there. And when I do this, I find some inconsistency with an interacting 4-dimensional SCFTs. When I try to lift these operators, I find that in 4 dimensions, they would have the wrong norms for being 4-dimensional operators in an interacting theory. So there is something wrong with the theory that lives here, and it cannot ever be an interacting 4-dimensional superconformal field theory. And so the bound is actually a strict inequality. Okay, so now let me reduce supersymmetry. Okay, of course, you see this and you would like to ask, can you improve this bound? But this is something that would go together with understanding. So if you just give me a random 2-dimensional chiral algebra, generically it will not correspond to a physically, well, you don't know the conditions for it to correspond to a physical 4-dimensional theory. And improving on this bound would probably require that you understand these conditions deeper. So, but now let me go down in supersymmetry and tell you how this also constrains the space of n equals 2 superconformal theories. So let me consider a 4-dimensional theory that has some flavor symmetry. In particular, let me look at SU2, the simplest thing you can think of. So in 4 dimensional, I'll have a stress tensor and I'll have flavor current. These guys, through their superconformal multiplets, will give in 2 dimensions a stress tensor and flavor current. And again, the same trivial statement I said before, hold, I know this 4-point function totally in terms of the 2-dimensional central charge. And I also know this one in terms of the 2-dimensional level. And they are related to the 4-dimensional counterpart. So I actually know these 3-point functions completely, and I can play the same game as before. Let me get 2-dimensional OP coefficients, lift them to 4 dimensions, impose unitarity. And what I get is this. So here I'm showing you like a slice of the space of n equals 2 series with an SU2 flavor symmetry. And I'm parameterizing this slice by the 4-dimensional central charge, so the 2-point function of the 4-dimensional stress tensor, and the flavor central charge, the 2-point function of the current in 4 dimensions. And these little dots here are series that we knew from before. So there's a bunch of them, but they all seem cluttered, like in this corner here. There was nothing here. And demanding unitarity of the UP coefficients you can read off from these things, you actually find that all these regions are analytically excluded. So you understand why there are all these empty spaces. And then you see that some series actually live in special points in these intersections. And these will, Pedro will say a few more words about. So this was just analytically. Of course, now we would like to put numerics on top of that. And we have done so only for this correlator. And sadly, it gave a weak bound. But we have the bounds that produced analytically these two red and blue exclusion curves were the whole set. So we should actually consider the whole full set of correlators and do the full-blown numerics for that. The problem is that we still need the superconformal blocks. So this is what really needs to be done before we can see how the numerics will improve on this situation. So now to conclude, I've shown you new constraints on the space of series with more than n equals 1 supersymmetry. And argue that there was no minimal n equals 3 series with this small central charge. Of course, we want to improve on this. So we want to start saying what is wrong with the series that has a central charge slightly bigger. Is there some inconsistency I can find when I try to interpret it as a 4-dimensional series? And this goes into a much bigger question, which is not fully answered till now, which are the conditions for a chiral algebra to correspond to 4-dimensional SCFT. So the example of why this series with this central charge failed to be a 4-dimensional series is like a first non-trivial example of what can go wrong when you try to lift, but the full set of conditions is not fully understood yet. And of course, then you can think that maybe I need numerics to actually move forward, and I should also try to complement this bound numerically. In particular, let me bring back this plot here. And there is a vast empty space here. So you see that series with increasing k have the C also to be bigger and bigger. So they are actually, so this blue, sorry, let me actually go back to the previous one where it's big. This green line here is just n equals 4 super Young Mills, seen as an n equals 2 series. It has an SU2 flavor symmetry. And so these central charges grow like along this curve, and all the series actually seem to lie to this side. And all this space here is empty. So one thing that seems to be missing is if there is some bound of this type that maybe you could achieve either analytically or numerically. And then we see all these series that live in special points in the intersections of the bounds, and you want to ask, can I actually start solving them? And for that, see Pedro's talk next. Thank you.
Thanks. Do we have any questions? Maybe, wait, anybody, yeah.
So what are the central charges of the non-n equal to 3 theories that are not n equal 4?
The smallest one is this number I quoted, 15/12. And then they get bigger. So they also come in families like with higher rank, with higher dimensional Coulomb branches. They have higher and higher central charges. And then there are various families. And this is the simplest one known to date, I think. It's actually bigger than n equals 4. The simplest n equals 4 is 3/4. And this number is bigger, which is not surprising. You'd expect less supersymmetry, you'd get a smaller.
Logan?
Sorry. So, can you say more about what goes wrong with this 13/24? Why can't the chiral algebra result be lifted to 4D? What goes wrong?
Okay, so when you do this procedure, the way you broke unitarity is that certain operators acquire negative norms, but we know exactly which operator. So if you give me a superconformal multiplet, I will tell you this gets a negative or a positive norm. And in this particular OP, the operator that was being exchanged, if I had an interacting series, there's only one operator that should be exchanged, and it should have, I think, a positive norm. But what I'm seeing in the 2D OP is actually two operators that are being exchanged, one with a negative norm and one with a positive norm, such as they cancel, and that's why the OP, so the bound comes from OP coefficient going to 0, but it's actually not an OP coefficient of one operator, but of a sum of two operators that have opposite signs in norms and just conspire to be 0.
Statement is saying that the 4D operators are not, they violate unitarity bound.
I think I would rather understand it in another way. So something I omitted a bit is that when you take this OP in 4 dimensions, there are two types of operators that can be exchanged. One gets a negative norm, one gets a positive. But one that gets a negative norm is a multiplet that contains higher spin currents. So I want to say that these guys are absent in interacting series. What I'm seeing here is that I'm actually forced to take both. To take a guy that a multiplet contains higher spin currents and a multiplet that does not. This is what the bound is saturated. That's why I said interacting.
Yeah, I have a very naive question. Does this tell us anything about the long-range easing model, which we just heard about, or it's a completely different class of theories?
You would mean like a supersymmetric version?
Yeah.
4 dimensions also.
In 4 dimensions, not in 3. Okay, okay. Yeah. Any other questions?
Since the new conformal field theory has a central charge that's larger than the n equal to 4 SU2, is there a way to make a flow that goes from one to the other one? From the high central charge to the low one?
Not that I know of, but recently there have been many these type of flows between n equals 2 series by some, so maybe not that I know of, maybe.